Okay, so let's look at problem 14 now. In this case, what we have is a graph problem. Same idea, same concepts. Let's try to look at what they're asking us for. So now they've given you a graph of the function h of x, that's given out here, and they're trying to ask you true or false that every relative maximum and a minimum of h occurs at a point where either h prime of c is 0 or it does not exist, whether it's true or false. So you have to figure out at every point h prime of c is 0 or does not exist as a relative maximum or minimum. Okay. So now let's try to figure out what are the relative max and mins, right? You have to see a little bump and an area where we have to see what's happening. So let's pick up the points where the function is not defined and the function is where this is 0. So let's draw a tangent here. The slope is 0. The function is not defined because of a sharp spot there. The derivative is not defined because of a sharp spot there. Tangent is 0 there. A sharp spot here. So now we have this all way. Now what we have to see here, for the first statement where they ask you whether for every relative maximum and minimum of h occurs at a point where h prime of c is either 0 or not defined. So the relative max and mins here, so if you're considering it for the first, let's start from the leftmost side, the relatively minimum, okay, is going to be occurring when this is 0. So this is okay. That statement is okay for that one. And then the relative max happens when it's not defined, so still okay here. The relative minimum right after that also happens when the derivative is not defined. And then the next relative max happens when the derivative is 0. Then right here when you see that function at that point in the middle is not defined, but that is not a relative max or min. Okay, so at this point you kind of have this idea that, oh, this doesn't make sense. So the statement that they mentioned for the first time, the every relative max and minimum of h occurs at a point where h prime of c is either 0 or not defined. Well, that's not a minimum. Okay, so we cannot conclude anything for that statement up there. Let's look at the other one for now. At every point where h prime of c is 0 or does not exist, so we're talking about all the points where you have all this. So all the points that we marked with the pink. We got to say that it also has a relative maximum or a minimum. No, at this spot, it's not a relative max or a minimum. It's just a little bump in the middle of the process, right? So what we say is the first statement is true, that every relative max and min that occurs at those spots, the relative max and min we figured out, all the black arrows happen to be matching up with the pink ones. So that's why the first statement is true. The second statement, however, says that every point where it's 0 or not defined, you should get a max and a min. That's not the case. At this spot here, what we circled, we do have a case where the derivative is not defined, but that's not a minimum. Okay, so that's why the last statement is false for the second one. Okay, let's jump on to the next one. Question 15. What we have here is a function where a, h, k are arbitrary constants. And the function that they're given us is f of x is a times x minus h whole squared plus k. Most of you guys, when you did it in pre-calc or in high school, this is an equation of a parabola. You kind of have it. But because we're just trying to assume that you guys know nothing, we're going to start to build this whole intuition from scratch. Okay, so let's say you had a function f of x as x squared. The graph of that will look like this. Everybody agrees with me on that at least, right? And now to be able to construct x minus h, all you're doing is you're trying to shift it towards the right. Okay, so whatever value you were supposed to get on 0, you're going to start to get it on h now. So if you had f of x as x minus h whole squared, all you did is you shifted that graph to a right, which has a 0 and that h value now. Okay, so let's do another operation. Now we're going to multiply by a. So now f of x when multiplied by that thing would just result in stretching the graph further. So it'll become more squishy like that. Still 0 to h. And final step will be to raise it by k. So now if you have f of x, that's all of that. But add a k, so you're going to shift this whole graph vertically upward, where this value is going to be k, and that value is going to be h. So all this is transformations from the function. Okay, so if a was negative, what you would get is a downward facing parabola. But because the statement in the question says that a is positive, we always know what's going to happen here. So I'm going to answer a bunch of things. So I'm going to answer the statements as in the order I read them. They say the graph of y equals to f of x is a parabola. The A statement is going to be true because it is a parabola, as we see that, right? And now the B statement is asking me an extreme value occurs at a point h comma k. Well, yes, it does, because we can see the extreme value, which happens to be a minimum in our case, occurs at the point h comma k. So the B statement is also true. The C statement in my case is saying if a is greater than 0, which means okay, we'll have an upward facing parabola, smiley face, then f must have a global minimum. Yes, that's true as well, because if you have an opening parabola towards the top, you'll have a minimum just like we had in this case. So that statement is true as well. Now we're going to talk about statement D. In this case, I'm expecting all of them to be starting to get false now, because we already got a lot of true of them. So now if a is greater than 0, then it has a global maximum. False, because we already talked about that. The maximum value of f of x is h. No. H is going to be a coordinate on the x-axis, so it does not tell you the maximum value of the function. So the statement E for me is also false. Let's look at the F statement and say the graph of y of f of x is a line. No, it's not going to be a line because we already concluded it's a parabola. So statement F is also false for me. And then G, none of the above, of course not. We're going to false that as well. So the question only asks you to pick the true ones. So just see accordingly which one works for you. I'm pretty sure you'll be able to get it very easily. Okay, so now we're going to try to find out some calculus to develop further ideas. So if you have this function here, let's just write it down here again. Ax minus h whole squared plus k. And now when you start to take a derivative of that as they ask you, remember to treat the a, h, and k as constants, only that function. So a stays here. According to chain rule, I get this 2x minus h times 1 because of chain rule. Okay, so that is my expression going to be. If you want to simplify this a little bit, that's going to be equals to 2ax minus 2ah. Okay, that's the derivative value. And then again, to find the critical value of that function, all you got to do, as we've been doing before, is to take the derivative and put it equals to 0. So when you equate this term equals to 0, you get 2ax equals to 2ah. The 2's go away, the a goes away, and you get that x equals to h is going to be the critical value, and we saw that in the graph as well. The critical value exists at the x coordinate of h. Okay, so now they're saying assuming that a is less than 0, so now we're having the opposite case of what we had. If a is less than 0, we have a downward facing parabola, right? And in this case, what they say is classify the critical point as the maximum or minimum. Of course, you can clearly see that is going to be a maximum. Okay, so that's how we finish up the problem number 17. Now, we're going to start to talk about problem number 16. problem 16 again, we have a function which they gave us to be 2x plus 6 over x. And then want to find the intervals where the function is increasing and decreasing. So we got to figure out the critical points of the function first. So let's take a derivative of that. And that's going to give us 2 minus 6 over x squared. And the points where this is going to be equals to 0, we're going to solve for the x values where this is equals to 0. So given that information, I do so, I make 2 equals to 6 over x squared. So equals to 3. And that gives my x must be equals to square root plus or minus 3. Okay, so the two values that I'm figuring out are going to be these ones. So keeping that in mind, we have to still do the test. So now we're going to, on the number line, we have square root of 3 negative and square root of 3 positive. So I'm going to pick a number that's smaller than negative square root of 3. So I'm going to pick up, let's say, probably 2, negative 2, right? Negative 2. So f prime of negative 2, when you evaluate that, you plug it in, you get 2 minus 6 over 4, okay, which is going to give you effectively a positive value, okay. So given that information that's positive, let's go to the next point. Let's pick 0 in the middle. You cannot pick 0 in the middle in this case because the derivative has a denominator of an x. It'll just go crazy. So instead of doing so, let's pick up 1. Okay, 1 is going to be less than square root of 3. So we can pick that up. When you pick up 1, you get 2 minus 6 for the actual derivative value. Let me just make it look nicer here. Of 1 is equals to 2 minus 6, so that's minus 4, which is less than 0. Cool. So now to figure out a point bigger than that, we're just going to pick 2, f prime of 2. It's going to give me the same result, 2 minus 6 over 4, which is still going to be greater than 0. My bad. So we figured out the interval, so I'm going to change the pens again. Figured out the interval that it's decreasing in that because you have a negative slope. However, in the other points it's increasing, so we have this interval, that interval where it's increasing because of a positive slope. Okay, so now you can answer all the things that they want to ask you about. What we can see is, okay, before we go that, we got to go back and say which one is a maximum or a minimum. Because these were the critical points that we figured out. The function shape is increasing to a max and then decreasing. So this is going to be your max value. Because before a max, your function must be increasing, and after a max, it must be decreasing to follow the behavior. That's why this is a max. However, on the other end, it's decreasing before, and then it starts to become 0, then becomes positive, so you have a minimum here. Okay, so now that we have all the information, we can conclude the results. So now, increasing on the interval where it's negative infinity to negative square root of 3, also on the other interval. So how do you write that here? Is you gotta use, hold on, let me see, read the instructions. So for your answer, it's either be a single interval, or it's gonna be like this. Okay, so the interval summation is gonna be like that. All you gotta do is make a comma and submit the other interval. So that's gonna be from square root of 3 up to infinity. Those are the increasing ones. The decreasing one happens in the middle, so it's from negative square root of 3 up to square root of 3. Okay, and we start to say the max occurs at x equals to negative square root of 3, and the min at x equals to positive square root of 3. Okay, and that's it. That's a wrap for problem 16. Now problem 17, kind of similar approach. Let's see what we have. Now we're going to start talking about double derivative tests. Okay, just a little fact I want to mention before that. So now I'm going to draw a function here, so we're going to look at that and start to conclude an intuition based on the graph of the function for finding whether you have a max or a min. So let's say you have this, right? And then this is the point where you have a max, and this is the point where you have your min. I'm going to use the green color to kind of find the behavior of a function. In this case, we're going to talk about the concavity. Okay? What we figure out is the point. If you have a maximum, the function must be concaving down like this, right? If the graph looks like that. It's always going to be this case. When you have a maximum, the function must be concaving down, or else you won't be able to reach to a maximum. In the other case, when you have a minimum, the function must be concaving up, right? So given that thing, how would you judge on concavity of a function? That depends upon the double derivative sign. Okay, so now we're going to conclude this here. If double derivative at a point A is greater than 0, okay, then it's concaving up. If the double derivative at a point A is less than 0, then it's concaving down. So now what we're going to do is we're going to test the double derivative at the critical points. So let's say we had a function here, f of x, and what this said is that it satisfies that f of 2 is 0 in my case. The derivative at 2 is also 0. And they've given us the double derivative at 2 is also 2. All we care about is the sign. So we know, because of this statement here, x equals to 2 will be a critical point, right? Because the derivative of the function at that value is 0. Now, because it's a critical point, we have to be able to classify it using double derivative test. We know if the function's double derivative at that value is greater than 0, we have a concaving up function. For concaving up, as we saw from the graph, we'll have a minimum here, right? So using that information, we can say because the double derivative is positive, because it is greater than 0, then x equals to 2 will be a minimum. It's pretty straightforward if you have the intuition from the graph, right? So you can pick up that value, and that's what's going to happen. Awesome. We're at the last problem. We got to use double derivative test to verify certain things. Let's get on and get done with it. So now we're trying to figure out the critical points and then use the second derivative test, if possible, to determine whether each corresponds to a local minimum or a maximum. Okay, so now the function that we have, f of x here, is technically x e to the power negative x squared. Okay, so in order to find the critical points first, we have to find the derivative and put it equals to 0. So let's find the derivative of this function. It might be a little tricky for some people, but it's going to be a product rule. So you're going to keep x as it is. Derivative e to the negative x squared is that, times negative so derivative of negative x squared is just negative 2x, my bad. Plus, what you got to do is you keep the e to the negative x squared as it is, times the derivative of x is just 1. Okay, so when you expand and simplify it, what we get is e to the negative x squared factored out will leave you with negative 2x squared plus 1. And this must be equal to 0 to find the critical points. So let's do so. When you put it equal to 0, the exponential can never be 0, so only looking for this guy to be equal to 0. So we get x squared, 2x squared must be equals to 1, which gives us that x squared must be equals to 1 over 2. So x, we got two possible values. That's plus or minus 1 over square root of 2. So I'm just going to make it nicer again. Alrighty, so once we have all of this, how do we conclude to the points that we want to? The first point they're asking us the critical point value. The critical point value is this. And the critical point value 2, we got those points. Now we have to test using the double derivative test. Okay, so let's take a second derivative of the function. let me just kind of write it nicely so we can have a good idea of what's happening. So the derivative function again that I figured out was just going to be e to the negative x squared times plus 1. So the double derivative will be again a product rule. So we're going to use that. The product rule will keep the e to the negative x squared as it is for now. The derivative of negative 2x squared is just negative 4x. And then you're going to keep the other one as it is, negative 2x squared plus 1. And the derivative of e to the negative x squared is just e to the negative x squared times negative 2x. Okay, so once we have this in front of us, we can still figure out that e to the negative x squared is a common factor for both of them. So let's factor it out. We get f double prime of x to be e to the negative x squared times minus 4x plus minus 2x squared plus 1 times minus 2x actually. So now we have to check whether at those points what's happening to the function, right? So let's try to expand it a bit and see where this whole thing is. We get negative x squared. Oopsie, let me just get rid of that. Negative 4x. You have negative 2x. A positive 4x cubed with that, right? So it's e to the negative x squared 4x cubed minus 6x. Alright, so when we're trying to figure out the value of the function at the points, we have to see which value is going to give us a positive or negative, right? In this case, this exponential is always going to be greater than 0. So the value that's going to be controlling its signs are this one. So let's try to plug it in. So when you plug in the first critical point, that happens to be negative 1 over square root of 2, right? What we get is, we get e to the negative x squared, e to the negative of that square root, but we don't care about that, it's going to be positive. So I'm just going to say it's something positive, okay, times when you have 4x cubed, so you get 4 over negative 2 square root of 2 minus 6 over negative root, so it's going to become plus of this, right? So in this clear case, you can see the positive value is bigger than the negative, since this is going to end up with a positive, which means the function is concaving up, which tells you that x equals to negative 1 over square root of 2 is a minimum. Okay, so we can apply the same test for the other case. When we do so, we'll get both the positive answers, and you see what I mean in a second. So now, our f double prime of x was e to the negative x squared 4x cubed minus 6x, right? So when you plug in the other critical point, which is 1 over square root of 2, you get something positive, which is the exponential of that number. We don't care too much about that, so we're not going to take care of that. However, in the other bracket, we have 4 over 2 square root of 2, then minus of 6 over square root of 2. So as you can see here, the negative value is going to be much bigger than the positive, so this is going to be less than 0, which tells us we have a concaving down. So when a function concave down at a point, we know that x equals to 1 over square root of 2 will give us a max. Okay? And with that, we can wrap up the whole problem. Okay, please feel free to message me if you find anything out of the place. And please bear with me. Cut me some first timer slack. I hope you like it. Thank you so much.